Hello, everyone. We're going to go ahead and continue with chapter 16. We last left off at question 21, so go to question 22. I'll give you a few minutes to get that open. I'm going to screen share and get myself set up too. All right, we're on question 22. So they give us a couple compounds that interact with light. They want us to give the intermediate. So we'll do that. So if you draw this, you'll have the intermediate. All right, so everyone should have 22 done. Not too bad. And then let's go to 23. '23 says they want the thermal product and they want the photochemical product. So basically we can ignore everything on the left-hand side, and you just have this. So something's gonna move here. One of the double bonds is gonna move. This will push this here. So the thermo product will be that's the thermal product. And then the photochemical product we're just gonna move, it just moves the direction differently, so we'll do that. So you have that. So the photochemical ring closure is disrotatory, and the thermal closure is conrotatory. All right, I don't see any questions, so we'll go on to question 23. Hopefully that gave you enough time to get question 24 done. Let's see. So 24, we have 1, 2, something like this. All you're going to do is jump double bonds. This is going to come here, make a sigma bond. And then the thing is, we have to know if it's going to be conrotatory or disrotatory. So it's a 4N process. Oh. So if this is 4N, we have thermal, we have photochemical, and this will be conrotatory, and this will be disrotatory. Just give me a second here. I'll look something up in the book real quick. Try to draw this the best I can. So now, for instance, if I have this color right here, and I'll draw this a little better. We have this. No, conrotatory would be we're going on the same side, and disrotatory would mean we're going opposite then. Disrotatory would be one of them's going to go here, the other, while this one's going to still stay the same. So that's your differences. So knowing that, let's see. So the photochemical product will have both the methyl groups up, while the thermal product will have one up and one down. So that's what we'll draw. Oh. Just make sure you have all the points there. I'm not the best drawer, but I try. It's in the wrong place. And then you just have to make sure you have all your double bonds. And then the photochemical product, same thing, except for the methyl group and the hydrogens will be displaced a little different. Here's your two methyl groups, and your hydrogens will be behind the plane. So remember, your photochemical is disrotatory on the 4N. You just look that up in the table. That's what I did. While you guys are putting that in, I'm gonna see what the next question says. All right, so let's go to 25 then. So we have this compound. You have a cyclopentyl group here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Always some double bonds in here. So we're going to label this position 1, and this obviously would be position 5. This will be position 1 prime, and this will be position 5 prime. So we're going to form a bond. These will move. This will go here. This will bust. Let's see. And this will come here then. So I don't even think it wants you to, it already shows you the final product. It just wants to classify the rearrangement. So the rearrangement would be a 5-5 then, because we're here and we form that bond right there. So it's a 5-5. We can do 26 on the same slide. Actually, we'll just use a new slide. All you have to do is put 5-5. So let's do 26 on a new slide. It says we have this compound. If you can draw this in a rearrangement, because this bond can, these bonds are free to rotate. Let me see. It's not writing for some reason now. So this can rotate. So if you rotate that bond, you're going to have something like this. I'm going to form a new sigma bond. This is going to come over and this will come apart. If that happens, then you get this. So Alice said, so if a new bond created encloses the structure, that's when we use the brackets, or can we use the brackets for other bonds? Let me see. Go back to that question. Open the book up real quick. So I'm on page 768, and this refers to this question right here. Let's go back. So if you go to page 168, this is topic 1610. It says a sigmatropic rearrangement is a pericyclic reaction in which one sigma bond is formed at the expense of another. It says in the process, the pi bonds change their location. It says the term sigmatropic comes from the Greek word tropos, which means change. It says a sigmatropic rearrangement is therefore a reaction in which a sigma bond has undergone a change in its location. So we did undergo a change in the location. We went from the 1 position over to the 5 position. It says there are many different types of sigmatropic rearrangements. It says the previous example is called a 3-3 sigmatropic rearrangement. And they talk about the notation then here. It says that this notation is different than any other notation used thus far in this book. The 2 numbers in the brackets indicate the number of atoms separating the bond that is forming and the bond that is breaking in the transition state. So that's the definition. So the 2 numbers in the brackets indicate the number of atoms separating the bond that is forming and the bond that is breaking. And figure 16.33 gives a good example of this. It says, if you look at figure 16.33, it says in the transition state, the bond that is breaking and the bond that is forming are separated by 2 different pathways, each of which is comprised of 3 atoms. And in this case, this is 5 atoms, right? In 16.33, it says one path is labeled in red and the other in blue. Therefore, it's called a 3-3 sigmatropic rearrangement. And then they give you another example. If you just look down at the next one, they say the following is an example of a 1-5 sigmatropic rearrangement. All right, you're welcome. So, that's just what I did. I just referred back to the book, just to give, a better definition of what was going on there. All right, so we have 25 done, 26 is done. Let me see, I'll leave that up. I need to. So we did our cope rearrangement here. Now we're going to go on to 27. So aliphatic, allylic, vinylic ethers undergo the Claisen rearrangement, complete the reaction. I'm just trying to think. Okay, so let's just draw this first. And we have some type of heat. We'll draw this on that side. Oh. So we can have some rotation on this bond right here at position 5. So I'm going to redraw that. So there was rotation right here. We'll just put this as rotation. Go here, here, here. So we form this aldehyde right here. And we have the 2 methyl groups coming off. So in the Claisen rearrangement, this is your Claisen. The sigma bond, so they're talking about this bond right here, between the 3rd and 4th atoms break. So we did break that. And a new sigma bond formed between the 5th and the 6th atoms. Sorry about that, between the 1st and the 6th. This sigma bond right here is going to form between the 1st and the 6th atom. We broke the sigma bond between the 3rd and the 4th. We formed a sigma bond between the 1st and the 6th. And that's a 3,3 sigmatropic rearrangement. And that's also on page 769. So if you go to page 769, there's a good explanation of the Claisen rearrangement there. you want to read page 716, I'll give you a minute to do that. And the reason why this happens is it says the equilibrium greatly favors the product because the formation of a carbonyl bond, which is thermodynamically more stable, lower in energy than a carbon-carbon double bond. All right, so let's go to question 28. So it says a specific steroid has a lambda max of 282 nanometers and a molar absorptivity, epsilon of 11,500 liters per mole per centimeter. What is the concentration? I think we're going to be using Beer's law. Let me see. So concentration equals so everyone's going to have different numbers here, I'm sure. You're going to have to put in your numbers. My numbers probably will not work for you. And the 1 centimeter is the path length. Here's your molar absorptivity coefficient. Remember, absorption is unitless. So in my case, I get 7.8. So that's what I got. All right. That was question 28 done. All right, so let's go to 29 then. So 29 says, which of these 6 compounds are expected to absorb radiation between 200 and 400 nanometers? So that's in the UV region. Anything beyond 400 is in the visible region, up to about 760. So let me see. We're looking for conjugation, so look for, now let's write that better for you. Which ones do you see conjugation? I don't know, if you guys are going to have the choices I have, you know, what do I mean by that? They could be at different spots. So you're just going to be looking for conjugation. Here's one. This double bond could be over a little better. There you go. So if your options C and F are not the same, you know, just know that, you know, you have to find yours that have conjugation. And what do we mean by that? You know, if this moves here, you know, you can move the double bonds. So if there is a positive here, this could, you know, move that positive charge over there. So we're looking for conjugation. We could put 30 on the same slide. It's a similar concept. 30 says conjugated systems absorb UV light. Select the true statement. So as lambda max increases, you know, you have your absorption, you have your lambda, and this is in nanometers. This is your UV region right here. Beyond that, this is your visible region. So as lambda max increases, the number of conjugated bonds in a molecule increase. So that means we're moving towards into the visible region. Here might be just 1, and here might be 10 over here. That's what we mean by that. 10 conjugated bonds. So as lambda max increases, the number of conjugated bonds increases. So whatever choice that is for you, that's the one you're going to select. We can probably even stay on the same one. Oh, 31. I'm not the best at, you know, drawing these things. It says, so if a compound is yellow in color, it absorbs violet. So it's going to absorb the opposite then, right? So what does that mean? That means, you know, we're absorbing in the violet region. If we absorb violet, then it's going to appear yellow. It's going to appear opposite. So we are going to select violet. That's correct. So certain compounds are visible if they have a bunch of conjugated bonds. Let me see if I can come up with an answer for that. So beta carotene. It has 11 conjugated bonds and it absorbs UV and blue light lambda max at 455. So that's why beta carotene will appear kind of orange, right? So it's going to absorb that light in the blue region, so it's going to appear orange. You can think, I guess, of carrots. So I see that many of you may have different choices than I do. So, you know, you just have to look on your color wheel and you have to decide, you know, which one's the opposite. So I know when I re-clicked back on the question that there was a different choice. So you need to look at the color wheel and decide which one you need to go to. So for instance, if you are absorbing a compound is green in color, you can't pick violet, you're gonna have to pick red. So there can only be so many options. So you just need to pick the one with your color wheel. So sometimes I see that students will say, well, I had a different answer than you, Dr. Buston, on the homework. Well, that's because you had a slightly different question than I did. They're all very similar, but sometimes they're slightly different. So you just have to kind of pay attention. So that's all 31 questions. So the question is, if the molecule is conjugated in any form, it will absorb UV. So in this case with beta carotene, since we can see it, it's beyond the UV life region, right? So, we have 11 conjugated bonds, so we're somewhere in here, right? So that means we're beyond it. All we're saying is if it has some type of conjugation, it'll start in the UV range. And as we become more conjugated, it goes into the visible range. That's right. It has to take into account the number of conjugated bonds. Because remember, beta carotene has 11 conjugated bonds, but yet we see it as orange, we don't see it as this colorless compound. It appears orange because it absorbs in the blue region. So, if you only have like a couple of conjugated bonds, it's going to be colorless. And that's kind of why I drew this I should draw it 1 to 11 here, not 1 to 10. So that's why I drew this 1 to 11. As you go over, you increase in conjugation, you're going to go this way. All right, I think this is a good time to take a break. Let's take a break till 11 o'clock. And then we're going to move into chapter 17. So the bonds can move. Let's just say, for instance, this takes on a hydrogen, right? And then you're positive here, and you still have this. Well, this can move here. If that moves there, then that positive charge now comes over here, right? You can do the same thing here. This can take a proton, positive charge here. It can move. And now when that moves, you'll have a positive charge here. So that's what we mean by conjugation. So let's reconvene between 11 and 11. We'll take about a 10 to 15 minute break, and then we will come back. All right, everyone, welcome back. We are on chapter 17. Chapter's titled Aromatic Compounds. If you read the chapter, they give you some simple examples right in the beginning regarding some aromatic compounds. They give you benzene, toluenes with the methyl group off, and orthoxylene. There's 2 methyl groups in the ortho position. A lot of benzene products are carcinogenic. I don't know if they mentioned that, but that is what it is. So that's a good question. So the question is, what chapters will be on the exam? It depends on how far we get with chapter 17. So we'll see, how we do with chapter 17. If we finish 17 tomorrow, then it'll be on the exam. If we don't, then we will push 17 back. Let me see. So aromatic rings are a common feature in drugs, and we can see this right here. Different examples of aromatic rings. It says coal contains aromatic rings fused together and joined by non-aromatic functional groups. It says benzene is generally the parent name for monosubstituted derivatives. So they're only one substitution. That's why they call it monosubstituted. So you have chlorobenzene, nitrobenzene, and ethylbenzene. They give you some more examples. It says the following common names are accepted by the IUPAC as parent names and are frequently used. So if you want to go into chemistry, or if you're taking one of these professional exams, you may want to memorize this. So if the substituent is larger than the ring, the substituent becomes the parent chain. So here, this is larger than the ring. Hept is 7. Phenyl group is just 6. So it now became the parent chain. And benzene rings are represented with a phenyl. You used to see me abbreviate this stuff. I'd either go like this or pH. Most likely I was doing it like this. So you can see where I got my symbol from. And that's the phi symbol. So for instance, if I had this and I put this over here, you knew this was a benzene ring coming off of that. So the common name for dimethylbenzene derivatives are xylenes. Xylenes are carcinogenic, just to let you know that. So you have the ortho position, it's just 1 down. Here we see it's 2 down, and then they're across in the para position. So the ortho, meta, and para, they're used for the location of the substituents on disubstituted benzene rings. So they're disubstituted because we have 2 methyl groups, right? And we're just putting a name to it. So it's ortho, meta, and para. So here we have ortho-nitroanisole, meta-bromotoluene, and para-chlorobenzaldehyde. So we already have a common name for this, right? Nitroanisole, but then ortho to it, I guess if we go back, I better go back myself. So the anisole is this right here. So we already have a common name for that. That's our anisole. So in ortho position of that, that's your nitro group. So this is toluene right here, and meta to that is the bromo group. Likewise with this, para is the chlorine group over here. And just give you some suggestions. So identify the parent, identify and name the substituents, number the parent chain, and assign a locant. says give the first substituent the lowest number possible. List the number of substituents before the parent name in alphabetical order, and ignore prefixes except ISO when ordering alphabetically. All right. So here, we have the parent is the phenol. So at the 3 position, the 5 position, we have bromines. So this would be 3,5-dibromophenol. Right. Either way, if you go this way or clockwise or counterclockwise, it's the same thing. They just chose to go clockwise. So you can practice here. So the first one, here's your aldehyde group. So this is going to be benzaldehyde. So at the 1, 2, 3, 4 position, you have a chloro group. So it'd be 4-chlorobenzaldehyde. Here we have toluene. Let's erase all this. Your toluene group is just that right there. So they're putting a bromine here at the 1, 2, 3 position. So it'd be 3-bromotoluene. And this is the one I couldn't remember. This is your anisole group. And, at the 2 position right here, they're putting 2-nitroanisole, or you could call it ortho-nitroanisole. It's whatever you prefer, Here's ortho, meta, and para, right? Yeah, so the question is, so if there's a common accepted name, so if you mean by this right here, we're going to put this as our, I guess your so-called parent name. That's right. So in this case, this is more common, and this is the anisole group. Because if we go back to these common names here, so that's all I'm going by. So we have the common name as the parent name, and then we put our substituents in front of that parent name. All right, so it said in 1866, Auguste Kuckel proposed that benzene is a ring comprised of alternating double bonds. So it's a flat structure. Kuckel suggested that the exchange of double and single bonds was an equilibrium process. Oftentimes you'll see it like this, and it's flat. It's a flat planar structure. Remember when we're talking about cyclohexane, we could have different formations of cyclohexane. Here's the chair conformation, you have the boat conformation, you have other conformations, but this is not a flat planar structure, whereas benzene is, and that's due to the resonance stabilization of the within the ring. And they show it to you right here. You know, these bonds can move. The resonance stabilized. So sometimes the ring is represented with a circle in it to avoid drawing resonance structures. So it's whatever you want to do. So aromatic rings are remarkably stable. Recall alkenes readily undergo addition reactions. And that bromine is going to come in and do an attack on the underside. It says aromatic rings are so stable, they do not undergo such reactions. So you're not going to see a reaction with bromine gas in this case, or liquid bromine. Bromine is one of those compounds that is a liquid at room temperature. So heats of hydration can be used to quantify aromatic stability. Here they have one double bond, here's two double bonds, and this would be the expected, but this was the observed. So there's a difference, and that's due to the stability of the bonds. And that's aromatic stability. And they say they can explain this by molecular orbital theory. So we have 6 pi electrons, right? You have each double bond is a 2, 2, and 2. So we have 6 electrons, pi electrons. So the 6 atomic p orbitals of the benzene overlap to make 6 molecular orbitals. So they're showing you this right here. This one is this one right here. And then you can have cases where, you know, this might be blue, and this one is blue here. This one's blue. So when you alternate them like this is this one right here. And you have cases where, you know, you'll have 2 reds. They don't show you all of these different ones. Well, I guess they do right here, but not like in the p orbital fashion. So the most stable one will be here. There's no electrons in the anti-bonding molecular orbitals, you can see though. So you have n atomic orbitals equals n molecular orbitals. So how many do we have? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And they're just showing you the different node locations. So not all fully conjugated rings have aromatic stability. So this is not aromatic, and this one's not aromatic. Some fully conjugated cyclic compounds react like normal alkenes. And you can see this right here. Remember when we had benzene, when we did this, there was no reaction. But now we're getting a reaction here. And see, we've shown you how to form cyclooctatetraene. And you do this with 2 cyclobutadienes. Yeah, so this has to do with the number of bonds, and this comes to Huckel's rule. So aromatic compounds must meet 2 criteria. So a fully conjugated ring with overlapping p orbitals. Okay, and we saw that right here. These fully overlap. And meets Huckel's rule, an odd number of electron pairs or a 4n plus 2. So, you know, equals the total number of pi electrons where n equals 0, 1, 2, 3, 4. It says the following compounds do not meet Huckel's rule right here. So this is the total number of pi electrons. So we're looking at cyclobutadiene, which has 4 pi electrons. So it lacks a closed shell, and cyclobuta, not cyclooctatetraene, that has it's also anti-aromatic. You can see where we put these electrons here. We put them in non-bonding molecular orbitals. We did the same thing right here. And if you notice about benzene, all the electrons are in bonding molecular orbitals, weren't they? So it says predicting the shapes and energies of molecular orbitals can be simplified drawing Frost circles to predict the relative MO energies. No, I never really got too much into this, but they just show this to you. It says for a 4-membered ring, you have a bonding molecular orbital for a 5. It's kind of interesting. So with cyclobutadiene, we have 4 electrons, right? So 1, 2, 3, 4. Well, we're above here, and we don't satisfy this rule, because if we would have put 1 here, this would be 4 plus 2, it's 6. Or if we put a 0 here, we'd get 2. So 4 is between 0 and 6. It doesn't meet the criteria, therefore, it's non-aromatic or anti-aromatic. So it says aromatic compounds fulfill the 2 criteria. They have a fully conjugated ring, and they also meet the Huckel's rule. Anti-aromatic compounds fulfill 2 criteria. They have a fully conjugated ring with overlapping p orbitals. So they do, both of these criteria are met. But here's where we differ. It says an even number of electron pairs, or 4n total pi electrons. And that's what it was for those 2 compounds, wasn't it? We're not going to meet Huckel's rule. It says when a compound fails criteria number 1, it is non-aromatic. So anilines are rings that are fully conjugated. So you can just say, okay, they have 6 pi electrons, 10 and 14. If we come back to our rule of 4n plus 2, two in here, we get 10. We put 3 in here, we get 14. This is working out pretty good for us. We get 6, 10, and 14. And the question is, so n in Huckel's rule just refers to any whole number. So let me see. So n just represents any whole number. So we're just trying to figure out how many pi electrons there are, So we're trying to figure out how many pi electrons. And n is just a whole number. That's all it is. So if this whole number that we put in here, if we put in, the case would be 0, 1, 2, 3, 4. We just put this in here. What do we get? We get 2, 6, 10, 3 times 12, 12 would be 14, and then 16, maybe 18 then. So n is just a whole number. So N does represent the total number of pi electrons within the whole system. So here you see this one right here. Here you see this one. There's 2, 4, 6, 8, 10. 2, 4, 6, 2, 4, 6, 8, 10, 12, 14. So the question is, so if we see these values in a question, well, let's just say I'm just going to draw this out. This is just something I'm just thinking about. Let's just say we had cyclooctane, or, it wouldn't be cyclooctane, but we just had it like this. Well, we see we have 6 pi electrons, right? But this satisfies Huckel's rule, but it doesn't satisfy a fully conjugated ring with overlapping p orbitals. So this is not going to be aromatic. This is going to be non-aromatic then. This is just as drawn right here, it'd be non-aromatic. Now, anti-aromatic is compounds that they fulfill the 2 criteria. They have a fully conjugated ring with overlapping p orbitals. Well, we have that right here. I kind of, if you do this little circle deal, you get this, right? You have 4 pi electrons, so 1, 2, 3, 4. And we have them in the anti-bonding orbitals, and you can even tell it's 2n plus 2, not 2n plus 2, 4n plus 2. We don't, if we put a whole number in here, 0, we're only going to get 2, and we have 4 pi electrons. So you can use this right here to tell you which one's in the anti-bonding and which one's in the bonding. In this case right here, we did have some that were non-bonding though. I want to point that out though. So in cyclooctatetraene, we did have some non-bonding orbitals. So this is where your atomic orbitals would be here. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 5, 6. And they're all at the same energy. So you have 8 electrons. And you start filling this stuff in. Actually, did that wrong. N atomic orbitals equals n molecular orbitals. So we have 1, 2, 3, 4, 1, 2, 3, 4. So that's a total of 8. So you have 1, 2, 3, 4, 5, 6, 7, 8. So that's how you get 8. And you just start filling the electrons in. So you have a total of 8 electrons in, right? So you just start filling them in this is your MO diagram right here. You just start filling them in. You have 2, 4, 6, 8. We see that we have some in our non-bonding molecular orbitals. But it says, however, if the structure adopts a tube-shaped conformation, it can avoid being anti-aromatic. So the conjugation does not extend around the entire ring. So you see, it doesn't extend around the entire ring. So the system is neither aromatic nor anti-aromatic. It is non-aromatic. Well, then in this case, when we had some non-bonding, then it was non-aromatic. So we can't assume that either. Let's see if I have any other examples here for us. So here we have 2, 4, 6. So with cyclopentadienyl, the anion, this is an aromatic compound. With the 7-membered ring, I'm just trying to see. What the? So you're saying this one right here? Well, that's because we had the 4n plus 2 rule, right? So if we put in 1 right here, this equals 6 pi electrons, right? And we got these extra electrons right here because it's a carbanion, and they can contribute to the overall structure. If we draw this like this, we're going to have overlap on all the structure, and this is what this is. So that's going to fulfill this criteria right here: a fully conjugated ring with overlapping p orbitals. So that's our first criteria right here. This is all overlapping right here, right? Then the second criteria is, do we fulfill the 4m plus 2? If we put a 1 in here, that equals 6. We have 6 electrons, so yes, we do. Now let's just say this was a carb cation. I'm just pretending, or just for instance, you know, does this fulfill this rule now? Now we go 4m plus 2. You know, we put a 0 here, so we can either have 2 or 6, and we count 2 and 4. If we put in our 4 electrons here, so we're still right here, but yet we don't fulfill that rule, so it's not aromatic then. So it can't be aromatic. And we come back here to this rule, where the anti-aromatic is, does it have a fully conjugated ring with overlapping p orbitals? So we could move those. So let's just move them. I'm just going to draw this a little smaller so I can do this. So if this goes here, now the positive charge is here. Well, if this comes here, well, the positive charge moves here. So the case of the anion, we have 6 electrons and we can fulfill the 4n+2 rule. And that gives us 6 because if we put 1 in here and it's fully delocalized. Now, if we talk about the anti-aromatic, we have 4n+2, which for a so for, we have 2 cases, right? We have this case right here, and we have 6 electrons, and then we're talking about the other case I just made up, which we have 4 electrons. So that does satisfy this, doesn't it? So this is a lot to go over, and we've run out of time, unfortunately. So let's continue this tomorrow because we're getting really close on time. So we'll continue this tomorrow. This is a really good discussion today. So I appreciate the questions. Just keep on asking questions. I think it really facilitates the discussion, and we can come back to think about this tomorrow. I'll try to get the homework posted today, so you have something to work on, and then we'll remember to, if you're listening asynchronous, I have to make this announcement. You have to keep up with the due dates if you're listening asynchronous. It's not an excuse not to do your homework, even if you were taking the class asynchronous. So please remember the due dates. All right, have a great day, and I'll see everyone tomorrow.